it's you versus Sean, and like,
yeah,
you know,
exactly,
like,
right?
just take the L, like 50% of the time.
I did. Thank you. Thank you very much.
And just move on.
That's exactly what I did.
Yeah. Okay. Round 2, Electric Boogaloo.
All right.
Oh my God.
Cool. Well,
Alright, where was it? Do we start from like...
Yeah, let's
we
start over.
start from zero. Just
Yeah.
for context, we just recorded the intro to this, and then Sean's fly was open the whole time. So. Oh my gosh.
Can't win them all, you know?
No. Okay. All right. Let me reintroduce the scenario. So, okay.
Yeah. Here, I'll take over. This is Sean.
Okay. Do it.
This is Sean Yeoh. Is that
Yeah.
the right? Yeah. So Sean works at AssetNote. AssetNote is an attack surface management tool, ASM.
Yep.
I'll let you
Yeah.
introduce sort of the background and how it became a thing and,
Yeah.
and sort of what spurred it all and go ahead.
Sure.
Yeah.
So ASM, or attack surface management, is like two big pieces. One is reconnaissance, which is understanding what your attack surface is. From our perspective, that's mapping out what is publicly facing. So what can we see from the internet? What DNS data do you have? What IP ranges do you have? And then more nuanced than that is things that you don't know what you have. So like what's running on the internet that we can attribute to you. So it's like, it might be random IP addresses that have TLS certs that point back to you.
Right.
Or like what we consider like cloud assets that you don't typically fall under what you can typically classify, but we have our heuristics to figure out this still belongs to you and it's still important. So that's the discovery piece of understanding like what's there. And then the part I think we do really well at is the security piece, which is now delivering value on top of what your attack surface is, finding what bugs do you have, telling you that these bugs are still there, and checking that continuously. So we will be sending not necessarily an obscene amount of traffic, but we do a lot of validation for very high signal bugs.
Yeah.
And I think a lot of the value people find out of our platform is that when we send you an email saying we found something, it means that one is exploitable and two, you need to fix it.
Yeah.
So, we ignore all the bullshit. We skip all the TLS findings, the cipher suites. Like, we only tell you that, you have an SSRF on your attack surface. We've found the exploit for it. Fix this. Or you have a exploitable version of Tableau running. We can validate the RCE. Here's the payload and the response for it. A lot of the value comes from the high signal and the reliability from how much coverage we get.
Yeah. And I guess just to add a little bit more context to that, like, we say Sean works for AssetNote, but actually Sean built AssetNote.
So Sean and Chubbs.
Yeah. Sean and Chubbs were the initial programmers of this tool. Yeah.
So the genesis of it was very much like we wanted to capture all of this amazing stuff that Chubbs already was doing. Like he was doing
in
this
the bug bounty space,
for the bug bounty space.
Yeah.
And he had this amazing pipeline where he was constantly discovering new assets on targets. He was getting notified on them and then automatically running his own tool set across these targets.
Right.
But then it's grown so much more than that. And I think in this process, there's a lot of things that you think is like, oh, it's pretty easy to just translate from bug bounties to an enterprise tool.
No.
But you learn so much more about it's a big difference from having something like, I need this to run, once a day or once a week or once a live hacking
SLAs
event.
or something.
To having this run every hour with an SLA and a customer being able to run queries against their data set that might be hundreds of gigabytes large.
Oh my gosh.
Whenever they want, for however much data they want. And getting from bash scripts and Python scripts to reliable production code is...
Did you know what you were getting yourself into here when you signed up for this?
I signed up to write tiny Go programs.
Right.
Yeah.
I remember I was in uni and I'd get messages from shops being like, I need you to help me write this thing. And I'm like, okay, sure, I'll write you a signature scan. That can't be that hard. What do you need to support? It's like, oh, we just need to send some requests. And I'm like, okay, that's easy enough. So one signature scanner later, we can send 80,000 requests a second.
Oh
Great.
my gosh, dude.
But now you have a different problem. It's like, all right, well, how do we run this? And it's like, we can't just have this DDoSing people constantly.
Right.
I mean, it's not even DDoSing; it's just one bot.
It's
So
just one bot
DOSing.
sending a bunch of.
Yeah.
So there's a whole bunch of like architectural learning we had where we've just like, as we sort of grown, we've realized that, you know, we went through the phase of let's just run everything on one instance to, okay, now we need to start like splitting up our services.
Yeah.
Not everything will scale the same way.
Right.
And it's like, well,
Okay.
So
So
we support all that?
let me pause you there for a second, because that's kind of where we want to go with that, right? Is like where I was kind of thinking we could go with this episode is kind of pick your brain for the bug bounty hunters out there. Like, what kind of architectural decisions would you recommend? Having sorted all of this, you know, for the past 5 years of your life, having lived the, you know, building this to scale, having lived, you know, going from the bug bounty phase to the full-fledged enterprise software grade, you know, where would you start? What would you do? What design decisions would you make? I know that that's a really vague question, but we can start with this. We were talking about message brokers earlier today.
Yeah.
Can you talk a little bit about message brokers, what kind of role they play in this architecture, and why you suggest what you suggest?
So, okay, I guess the first question is like, what is a message broker and why do people use them?
Right.
The answer, like, there's kind of two ways of doing things when you're trying to automate things or build a large system.
Yeah.
The first thing is you can do things synchronously. So it's like, I want you to, you know, give me all the subdomains and scan them. So you would just like run a script that gets all the subdomains and then run a script that scans all of them.
Right.
That's okay.
Sequentially.
Yeah, sequentially. That's okay when you have like one set of things to do. But when you want to be like, I want to see this every hour on the hour and have like hundreds of thousands or millions of hosts to do, you're going to have very, very long running scripts. And you'll probably like, you know, for 100,000 or 1,000 hosts, you can probably run it in one script and get it done in an hour. Yeah. But when you enter the phase of like millions, tens of millions, hundreds of millions of hosts,
which does happen in bug bounty. I've run scripts that were against 3 million hosts. You know, in the bug bounty programs that I have access to.
Yeah. And like you might have heard of things like Axiom that'll help you parallelize these things.
Yeah.
That's fine. But at the end of the day, you're still like, you run them and then you collect them and then that's kind of it.
Yeah.
When you move to the realm of like, I want to start having things like pipelines, then you will start venturing to a lot of things like RabbitMQ,
right.
Or like Amazon SQS, or all of these different like queuing services. And that's kind of what message brokers are. It's a way of queuing up a whole bunch of things, with what we call producers. And then you have a whole bunch of services or like programs that start taking things off this queue and consuming them, hence consumers. And that's sort of the role the message broker fills.
Okay, so the message broker is you have various pieces that you want to work asynchronously. So let's say you've got your subdomain tool, and every time it finds a subdomain, it like pushes a message out to the message broker, and that message gets sent out to the other microservice that's going to do scanning, and it gets sent to another microservice that's going to do, you know, it's going to pull the TLS cert, and another one that's going to like pull the HTML page, right? Is that that's the idea, right?
Yeah.
Okay.
So yeah, it's pretty much like
it's the glue.
Yeah, it's kind of like the glue or the way you get messages around.
Yeah. It's the mailman. You put a letter in the mail. Mailman decides, you know, well, it's not quite that, but it's more generic than that.
Yeah.
But
it's pretty much the idea. Like, you know, you chuck the mail in.
Yeah, the principle of that, yes. You're sending a letter out and then many people will receive that same letter. That's where it varies.
Joel, you know the rule. We don't do live analogies here on Critical Thinking Podcast.
Ignore that.
Every time. Don't laugh, Mariah. My wife's over there laughing because I suck at analogies. No, every time I try to do an analogy live on the pod, it's terrible. But okay, so we've got these message brokers. They're fanning out, you know, system or the messages to all the different pieces, or you know, I guess we were talking a little bit earlier today about event-driven sort of architecture, which is not necessarily different from that, but is, I guess, more different at a conceptual level than a... Yeah.
So event-driven architectures, and pardon me if I'm wrong, but generally the idea is there's sort of two ways this organically grows out. One way is that, and very much if you're doing your own thing, you'll sort of fall into the first category as opposed to the latter.
Sure.
The first category is like, I've got these things I want to do. So I want to get TLS certs. I want to do a port scan. I want to get a HTTP title, right? So you have ideas of processes or programs you want to run. Right. So then you sort of build out your queues, or whatever your like message broker partitions, however you want to call them, based off these tasks. And you say like, I'll have one queue for TLS certs. I'll have one queue for ports, one queue for titles. And the outcome of that is pretty much almost each service you think of will eventually have a queue by itself. But I think the other way is event-driven architectures, where you very much think about what kind of data am I working with, right? It's like I'm working with subdomains. I'm working with IP addresses. So you start flipping the model and thinking that when I discover an IP address, then now I can start informing things like I want to start a TLS scan on it. I want to start getting titles from it. And it's a slight nuance, right? Because you're no longer thinking about like, what am I trying to do? But it's so much more, what do I have?
Or what is already happening?
Yes.
Right?
What is happening? And then what do I want to do from those events that occur?
Okay. So an example of that, and that we were talking about earlier today is like, let's say we have a, I guess we could say SLA, but it's not really that in our bug bounty context. Let's say we have a desire to have an updated picture of DNS on all of our assets every 5 minutes, right?
Yeah.
When that 5 minute or maybe when that 4 minute, 45 second, mark comes around, we can trigger an event that expires our current DNS representation, and that event can trigger various different activities. Is that how I'm understanding it?
Yeah. So, I mean, you can go one way of like saying when things expire. Usually it'll be things that happen. So you might say every 5 minutes you'll do a DNS resolution of all your assets.
Okay.
Right. And then
that's an event.
Yes. Right. So the event would be like, we've discovered this subdomain maps to this DNS record.
Okay.
And that's the event.
Right.
Right. And then now, like part of that event, the data you have is a subdomain and IP address.
Okay.
Right.
So how do you stop the subscriber services from basically just becoming bottlenecks themselves, because you have like one thing doing one thing, but it may need to do a lot of work to do that, right? So like say you have one thing that's doing the DNS resolution, another thing that's doing getting the HTTP titles and so on, right? What DNS resolution might take significantly longer.
Yeah.
And so one of those things may be bottlenecked just because it's going to take long. How do you get around that?
There's a couple ways. I mean, one is you can go faster. And like a lot of time that we've spent, at least in the couple of years I've worked, is you start heavily optimizing for these things, right? You realize that detecting technologies is taking like, 30 seconds to a minute per website.
Right.
That's forever, right? So you start optimizing that aggressively. Can I get 60 seconds down to 30 to 20 to 10? At some point, you are bottlenecked by the technical limitations.
Right.
But once you get to that point, it's like, okay, now I'm already 6 times faster. That heaps better. But then the other side is sort of what you're leading to is now scaling outwards, right? You can start partitioning your work into smaller pieces. Instead of resolving all 300 million DNS records you have at once, you start sharding them up and say like, I'll have multiple workers starting to create events, right? I'll start scaling these out, parallelizing them, creating replicas a la Axiom SH or whatever the website is for it.
Sure. Yeah.
And then now you can have 300 workers each resolving a million at a time.
Right.
And then as you sort of create all of these shards, now you sort of get over these issues of throughput.
Okay.
The other side is you sort of can do architectural decisions with the tools. So instead of just having one big bulk result in one big bulk of data, is you start streaming the results out.
Sure.
So it's more like the tool in itself is also asynchronous.
Yeah.
And then you have a continuous stream of things. But depending on the scale, you kind of don't really need to make all of these optimizations.
Yeah. So I was actually just about to add that. Like, so this episode, and I think the lessons that we're learning here from Sean, this is him doing this at an enterprise grade scale. Right. And for, like we talked about on the pod before, like a lot of bug bounty stuff is literally just duct taped together with crazy
nuclei
stuff.
Scripts.
So don't feel like you have to do this unless you want to, unless it's your thing to like write cool. Do you disagree with that? You're making a face.
I make the face because I think it's something like...
Because you do that shit? Is that why? Oh, wait. Yes, it is. Because I've lost to Sean's recon scripts before. I mean, speed.
I over-engineer because that's my day job.
Yeah.
My job is to build this for the enterprise. I beat you in DNS recon because I need to for work.
Yeah.
But I think if you're one person doing this I have a team of people supporting me.
Right.
When I say like, I build a service that shards it up, runs asynchronously across a message broker. I have a team of 2 incredible like infrastructure engineers that maintain 60 Kubernetes clusters.
Oh my gosh.
Right?
Yeah.
I have a team of 5 engineers that help me build software to do all of this. Mind you, I don't use AssetNote for bug bounties.
Right.
We do this for our enterprise customers.
This is an enterprise grade thing.
But when I'm talking about these problems we're having, they're very much similar to what you see in the bug bounty space.
Yeah.
And I think when people say that you can't scale beyond this or like this tool doesn't do this, I think that's a limitation of time and effort, not a limitation of the tool.
Yeah.
I think you can solve technical problems of like, oh, you can't scan this fast or you don't have this data.
Yeah.
You just need to be able to invest the time and energy into it.
Yeah, that's one of the things I really like about talking to you too is like we, I feel like the question for me a lot of times is like, all right, well, this isn't moving fast enough, so I'm going to scale outward and then you bring a refreshing perspective. Well, what if you tuned mass scan to actually just be able to go, 6 or 7 times faster. And then that just solves all your issues magically. And it's not necessarily it's even more intriguing to be able to dive deeper into those problems, because in order to tune it, you have to understand it at a lower level too, which I think fosters a lot of growth as a hacker if you do that.
It's a very, very different skill set though.
Yeah, it is.
And I think but I also think that's like a really good way to look at it, because like if you think about it, right, if you have like a really inefficient system, instead of just multiplying that system to try and make it more efficient, optimize the system and then see if you need to multiply it, because you're going to have cost savings, you're going to have scaling savings. Like like that lack of multiplication is going to save you in so many other areas where instead of having to like use an inefficient system multiple times in a row to like compensate for the lack of optimization, you can just solve that by optimizing and spend a little more time doing that instead.
Yeah, it feels so good too. Like when you get something optimized, like I did this once, right? I rewrote like all of my other stuff is like garbage, like it's Python taped together, Python 2.7, mind you, taped together. But this one time I was like, you know what? I don't know why I fixated on this problem so much, but I literally was like, all right, you know what? Aquatone, it takes a picture of the, the website, and then it downloads the TLS cert. And I was like, you know what? I want to do that in one TCP connection.
Yeah.
And because it was making 2 TCP connections, and I was like, for some reason that day it was like killing me.
Yeah.
So I like wrote this whole thing with Chrome DevTools protocol to like grab the TLS certificate from Chrome DevTools protocol and then also take the screenshot at the same time. And it was not that much faster. And but I felt great.
I was going to say, it should be like 2x, right?
Yeah, it's like, it wasn't even that. I mean, it was...
I mean, you'll find anything involving Chrome is this black box of time and effort.
Oh, yeah,
We've
for sure.
spent months, because the only way you really can do proper technology detection is you need to evaluate JavaScript.
Right.
Yeah. And there's been all of these solutions that try to get around it, but at the end of the day, you kind of need to run a browser.
Yeah.
And we've spent countless hours trying to shoehorn existing solutions into an enterprise context. At some point, we're just like, fuck it.
Yeah.
We'll just rewrite it.
Yeah.
Right?
And do you ever draw that line where you're like, this isn't worth the time and effort, or is the juice kind of always worth the squeeze?
We always start with the simplest solution. And almost everything that we've implemented will start with, what can we do that gets us 80% of the way there with 20% of the effort?
Mm-hmm.
Like AssetNote started as Python scripts around existing tools. And then as we sort of grew, I mean, that's the origin story of every automation platform.
Yeah.
Anybody who automates does that.
I think like, if you're doing it yourself, that's 100% where you should start. And you should not start from an event-driven architecture or like an auto-scaling Kubernetes system.
Yeah.
You should start from janky Python scripts that that automate what you're doing now.
Okay.
Into something quicker.
Have you ever seen that XKCD about automation?
Yeah.
Oh, I love that table.
Yes. Okay, we'll put it up on the screen. But basically, there's this XKCD graph.
What's the timestamp? What is the timestamp? I'm gonna have to write that down so we don't forget. Okay. All right.
Okay.
2020.
So basically, there's this XKCD graph, right? It's like what people think automation is going to do. And it's like, you do a little bit of automation, slows you down a little bit, and then you exponentially get faster. And in reality, what happens is it gets a little bit faster, and then you lose all of your productivity trying to maintain that tool and trying to make it better. And like, you spend so much more time fixing and working on the tool than you ever spent like actually getting the benefits from the automation.
Yeah.
And I think that's like perfectly exemplified by what you just said, because it's so easy to fall into that trap where you're like, I really need to do this perfectly. I need to like build the best, fastest way to do simple task A, right? Yeah. And instead, you should just be like, there's this acronym KISS, keep it simple, stupid, right? Yeah. And just keep it simple. Just 80% of the work, 80% of the result, 20% of the effort, right? Yeah. It's just like so much easier to start from there and then reevaluate and iterate on where you're at.
Oh, 100%.
And just like iterate until you hit a wall. And then iterate again, and then...
I think the best results I've gotten from all the automation stuff was not actually spending time planning out a whole architecture, was just running it and every week sitting down like for one day that week and asking like, why, or like, has this been effective enough this week? And I think we had a period where we were competing on some takeovers, right?
Yes, we did. Yes, we did.
It would go back and forth every other week of seeing like who was getting more takeovers or whatever. And the process literally was like every week I'd ask myself, has this week's yield been sufficient or do I need to spend time making it better?
Right.
And the weeks that I made the most progress in making it better was when I had the lowest yield. Because there's no better motivator for you to make something
than knowing Justin's getting loaded.
No, that somebody else is making your money.
So how do you evaluate, like at an enterprise level, when you're trying to optimize, what are you doing to figure out where those pitfalls are within your application?
Right.
How do you analyze that?
Right. And so, you know, we've done our disclaimers. Now we get the real reason we have him here, which is for you freaks that love to code, love to optimize, and want to be, you know, win your bounties and bug bounty by being the fastest and over optimizing. Voila. Here we go.
Okay, it's a very different scale when you're operating across. So to explain a bit, like, okay, to not disclose our entire architecture, at a high level, we scale out our services across hundreds of replicas, across hundreds of EC2 instances.
Right.
And profiling and, I guess, observing the data there is very different from running something on one machine. So in our case of like me running my own stuff, I would just have one EC2 instance that's running this one program that does, you know, whatever takeovers they're doing. Right. In that case, it's pretty straightforward. I can just attach a profiler, use the inbuilt Golang profiler, and start looking at, okay, where's time being spent? How am I using it, etc. Right? And just do some basic programmatic optimization.
Okay, so I'm gonna pause you there because I've never done that. So essentially, what he's saying, and of course, you just attach the basic profiler. No, and so the profiler is something that tells you what operations are taking the longest in your code execution? Or?
Yeah, so what a profiler does is that it records what's happening in your program.
Okay.
With a small amount of overhead. I think Golang is probably in the realm of like 5 to 10% at worst. I think now it's in the realm of like 1 to 2%.
That's great.
So effectively what it does is it sort of takes a whole bunch of snapshots. Every millisecond or every second, it'll take like a whole bunch of snapshots and ask like, what is running at this moment? And then what you do with all of these snapshots is you aggregate them together and then it tells you at this point in time, this function is running. And this function took 7 seconds to run, right? And you can start seeing a heat map and they have all of these great tools. I think there's a great like flame graph profiler that shows you exactly how long is it spent in each function over a given period of time. And the value of that is that you sort of start to very clearly see where time is spent in your program. Am I spending all that time waiting on a network request? And if that's the case, then maybe I can spend like more network requests at the same time waiting.
Sure.
Right? So you can start parallelized horizontally. And then you might start hitting a bottleneck of, oh, I'm actually no longer spending all my time waiting on network requests. I'm spending all my time in these like 3 lines that is actually just looping over all the subdomains really, really fast for no reason. Right? So maybe I can start skipping out of that loop or restructure it so I don't need to loop over that so many times.
Sure.
And you sort of slowly start to understand why my program is slow. Right?
Yeah. Wow. I love that actual data-driven approach there. Yeah. Like for me, if I were to try to do that same thing, I would look at the code. I'd be like, okay, where's it slow? You know, I would just kind of guess. You know,
that's what the early days
are for, right? Right. Like that's their whole reason. I think you see this a lot of pure engineering companies. Is that like this is very common practice?
Yes.
Where it's just like you have a system that needs to run at scale just due to user demands.
Yeah.
And in order to make it work, you have to figure out where it's being slow and make it better and optimize it just to simply function.
Yeah.
Whereas it's almost like that, but it's to like another level where it's like, it needs to function, but also it needs to be like the best, right? It needs to be better than the best. So how do you make it better than the best?
I mean, you know, if you want to go the next step after that, like at some point, profiling just your program isn't enough, right? Because like at some point, you're going to start, when you start doing a whole bunch of networking stuff, you start asking questions like, well, how do I interact with the network? Right. And like the obvious answer is, okay, you can make the network faster. Right. But this comes back to like that question of what happens when you type in google.com? Like how many layers deep do you want to go?
Yeah.
Gosh, dude, it's so funny you mentioned that because we literally talk about that all the time, you know, and it's literally like, that comes, having a core understanding of how that works is just absolutely pivotal to everything. You know, you have to understand every single detail of that.
Yeah. There's a great GitHub repo that goes over like all the way
different stacks.
Yeah, it goes all the way to like the key press, and it's like an electrical signal is fired when you push the key down. It's like,
oh my gosh,
yeah, it's really good. We'll link it.
We need that. That's amazing. I've never heard of that. I'm going to text you right now. That's
back when I was in like university, that was like all the interviewers. They were like, you know, they're going to ask you what happens when you type Google.com in a search bar, and so like, you know, that was something that you would just like memorize. It's like, Dude, does DNS look up? And then, I
feel so validated right now because like I never knew that anyone else like put as much importance on that. Yeah. Like that's where I start with everything. Like, and oh man, that's.
I mean, don't get me wrong. You can go very far in the other direction of like over optimizing for this. Yeah. And it kind of depends on what you find fun. Like sometimes I find fun in just doing all of this stuff. Mm-hmm. Other times, like, you know, you probably should be hacking instead of fiddling with the kernel.
Exactly.
But I can imagine that at like AssetNote scale, even the very, very marginal optimizations are going to be super worth it because of the scale that you're operating in.
So one of the current projects that one of my engineers is working on is one of the features that we have is integrating with like your cloud services. Mm-hmm. So integrating with AWS or integrating with GCP. And we've just onboarded a customer that...
For pulling assets in?
Yes. So like we ingest all that data, we help enrich it, give you extra information, and then that sort of feeds into the whole platform that we have. One of my engineers is currently working very closely with the customer because initially when we built this feature, we were like, okay, approximately what scale can we handle? And a big question that sort of you mentioned earlier, data-driven decision-making, is like understanding what performance properties are we looking for when we build this? What are our expectations? What can we handle? A customer came in and we're like, okay, we set a reasonably high number. It's like 10 times more than whatever any of our customers are doing.
Sure.
They came in and onboarded with 10 times more than that.
Oh no.
And like, you're joking. There's no way. We spoke to them and they're like, yeah, it turns out AWS had an internal limit and we had to ask AWS to bump that limit.
Oh my gosh, dude. You can't even rely on the AWS limits.
So we estimated pretty good, right? Like we estimated to what AWS's maximum public limit was.
Sure.
They're above that by another order of magnitude.
Wow, dude.
So he's spent the past few weeks optimizing our service for synchronizing this an inordinate amount. Like, our average expectation is we should be in sync with you every 5 minutes.
Yeah.
Right.
Yeah, that's a good expectation.
Optimizing this 90% got us down to like 10 minutes. Right.
Wow.
And when you already optimized at 90%, to get another 50% on top of that,
it's huge. Yeah.
Is
it's very
an
challenging.
Unbelievable amount of optimization, work to get there.
Oh, yeah.
And now you're looking at just like, well, what is all the micro optimizations can we be doing? Can we be like, not making requests for things that we don't need? Can we be turning off requests that we know are immediately going to fail? Yep. Can we start pre-caching requests?
Oh my gosh.
We hit a second entire set of limits we didn't realize existed on assuming role between AWS accounts.
Okay. All right. Recorder died.
Yep.
Jump back in.
All right. So jumping back, I guess we needed to get back on track anyway. So, all right. So bringing this back to the discussion surrounding if you were going to...
That's spicy.
Did you?
Final destination?
What the heck? Did you think that was what that was?
All right.
All right. So,
What is it?
The ghosts are not happy that we're revealing the optimization secrets right now.
Right. Oh my gosh. Okay. So Mike died. We're getting back to the topic here. So just bringing it back around, we want to try to bring it back to bug bounty and get some architectural wisdom on this. So we already talked a little bit about message brokers and the role that they play and using that in order to build an architecture that allows all these different microservices, which perform all the different tasks like performing scanning and DNS resolutions and, vuln scanning, all that. Those get sort of sent and connected by the message broker. What kind of message brokers would you recommend, and what other pieces of the stack would you recommend that it would save us a headache that you learned over your years of engineering, this sort of thing?
It depends on how much time and money you have.
Right.
I think a lot of things you'll see is like SQS, RabbitMQ.
Yeah.
I think those are okay solutions if you need something now. Actually, I wouldn't recommend RabbitMQ.
Yeah,
if
just
you need
don't do RabbitMQ.
The reason being,
Yeah.
it's very difficult to keep alive. And
Yeah.
then once you start getting to a certain scale, there's an excellent blog post. I need to dig it up somewhere. I might link it to you.
Yeah,
Where it
please.
says, don't use your message broker as a database. Right?
Yeah,
Yep.
yeah.
And
That's
the idea
yeah.
being that if a message is sitting in your message broker for too long, then now you actually are just using your message broker as a database instead, which
right.
you shouldn't be doing. The idea is that your message broker is where you queue things up and then those things get consumed. So it eventually should try to get to zero.
So what do you use to store those messages when they're in the queue?
So we do use the queue, but the idea is that you should have enough processes to make sure your queue is being consumed.
Okay.
Yeah.
Right? And if you're seeing that your queue is only going up, what I recommend is like for a message broker like Nats, which I think is a great piece of software for this because it's relatively lightweight. It's got a whole bunch of different SDKs for you to implement against, and it's relatively
NATS.
Yes, NATS.
NATS.
It's pretty good for this, and there's a whole bunch of other projects adjacent to it that help it. For example, things like Keda, Keda.
Okay.
So if you are using Kubernetes, this is
Right.
a great way to scale it. So Nats is a great solution. You might also have like things like Redis. The only difficulty with Redis is that it's very hard to get good visibility into it. Right?
Oh, really? Okay.
So
That's very important.
if you're asking questions like, how long has a message been there? Or when should my messages be expiring? Redis may not be the best solution because you need a whole bunch of other things to manage that for you. Redis is really good at what it does, which is be a key value store and give you really accurate results really quickly.
Right.
But for something that you actually want to use as a message broker, things like Nats have a whole bunch more features, saying things like, I want to expire messages that are there for more than 24 hours.
Yeah, man, that would be clutch because even if you do get a system clogged up, right?
Yes, you want to have some way of making sure it doesn't DOS the rest of your node.
Exactly.
Right? Like you need to have all
That's
of these.
the problem I was having with RabbitMQ.
Yes.
Yeah.
Like it will run up all your storage and then shit, my disk's full, my system's dead.
Yeah.
Or it will run up all
Buy
your RAM.
messages.
Yeah, goodbye all my messages, goodbye everything else that's running.
Yeah.
So you do want to set yourself some limits. Understand that, okay, I want the maximum capacity to be 1 gigabyte of memory.
Mhm.
I want the maximum disk space usage to be 15 gigs.
Sure.
I want the maximum age of my messages to be 24 hours.
Mhm.
And if things are taking more than that, then I've got a problem with my code.
Anyway, yeah.
It's not a problem with the message broker.
Right.
So there's that piece to it.
And one of the things that I learned from the message broker era was like, when I was working with it was you really want to make sure that you're consuming at a faster rate than you're getting things published into, right?
Yeah.
Like, you alluded to that earlier that, it needs to hit zero. And even when you've got a bunch of data coming into your pipeline, like as long as you're consuming at a faster rate than you're adding to it, it should be going down. And that's what you want to see.
I mean, of course it can have spikes.
Right.
Because naturally some things will have more spiky and like, what do they call seasonal trends than others.
Sure.
But yes, you should be aiming towards, at some point it should be able to hit zero. And if it never hits zero, then now you have a question of why is it not hitting zero? Is something taking too long or I'm not scaling it out enough?
And then we go back to optimization.
Yes.
Right?
Yeah. Okay, so we got Nats and Keda.
Keta's great for scaling, but it's mostly Kubernetes relevant.
Okay.
And if you're running something yourself, probably don't use Kubernetes.
Right.
I have a team of people. I mean, at one point it was just me managing a lot of Kubernetes.
Yeah.
I'm sure that was fun.
Fun's one way to put it.
Yeah, dude, I did a Kubernetes cluster for my microservices when I was doing this architecture, and it was a lot of problems, And I think one thing that we talked about earlier was like trying to run mass scan or any really performant scanning from within a container is just not going to happen, right?
There's a whole bunch of kernel tuning you need to do to make that work.
Okay.
So one of the most common problems you'll hit is what they call a contract limit.
Okay.
And what a contract limit is pretty much when you're making connections on your operating system.
Mm-hmm.
What your kernel needs to do is be able to track what packets going out and coming back actually belong to us. Right? Like your kernel doesn't want, when I send out a web request for google.com, for Joel to start sending me traffic and then intercept my google.com request and then poison that, right?
Sure.
In theory,
Yeah.
Right? So what they do is they track all the IP ports combinations going in and out.
Yeah.
And things that are not relevant, they just drop.
Right.
And that's what they call a contract. And there's a big table that tracks all of this.
Mm.
What a contract limit is that this table can fill up. And this is very like likely to happen with port scanning, because what are you doing?
You're just spanning a bunch of
IP addresses
yeah.
and ports, which are the two things that contract tables rely on. right? And when you're doing it across millions of hosts, across tens of thousands of IP addresses, your table is going to be full really, really quickly.
Mm-hmm.
And
is that contract table at a host level or a container level?
So depending on how the networking you have is set up, if you're using like Kubernetes level normal container networking, you'll have two different IP address spaces, right? You have the pod IP address space, and then you also have your node's IP address or the instance's IP address.
Sure.
And then now you need a translation layer of when a web request goes from the pod, when a packet goes from the pod to the instance and then out to the internet. Now you need to translate that NAT back into the pod. And if you're not sure what I'm talking about, network address translation allows you to have multiple IP addresses behind a big IP address.
Right.
It's how your router gives you an IP that is not connected to the public internet.
Yes. Yeah. And in Kubernetes, it's kind of the same thing. Your pods need to get an IP address that's not connected to the public IP address. So they have that translation as well. So this actually happens on the kernel of the instance. And that means that when you're from a pod flooding the internet with a whole bunch of packets, that means that these are all being translated by your kernel between the pod's IP space and the instance's IP space. And then at another level, if you're using something like AWS, there's another one for AWS translating between your private IP space and the public IP address of the internet. And each one of those is its own bottleneck.
Right.
And you'll often see, and you probably hear this very often, if you try to mass scan, suddenly your connections start dropping. Your
everything just disappears.
Yeah. Yes. And it's like, it's super unreliable what's going on. It's because of this. So what do? You move container networking from the pod to privileged networking. Bad for security, good for performance.
Sure.
Right. So you get rid of one layer of this. Then the second part is you move your instance away from any sort of natting from like private IP ranges to public. You just slam it directly onto the public internet.
Okay.
Right. And then that means that there's no sort of bottlenecks between you and the internet unless you've got like an ISP level CGNAT.
Sure.
Which is where your ISP itself does more natting. So maybe you ask them, can I disable CGNAT or opt out or find a different ISP?
It's absolutely like one of the reasons why I so value these conversations with you is like, do you know how long it would take you to get to that level where you understand each one of those steps about, you know, the contract table and the kernel optimizations and then all this various level of natting. And like, it's because you have been at war with these problems for the past 5 years.
Oh, yeah.
And man, it's just such a pleasure to be able to sit down and skip all of that. And so, yeah, that's great. So you solve that by putting it on, you know, outside of the Kubernetes cluster, putting it directly onto a box that's on the internet, as little NAT as possible, as little bottlenecks as possible. And then you can do more efficient scanning that way and then publish it back into the message broker or, you know, I guess this is another question. This is a little bit of a, I don't know. We won't go too far down this rabbit hole, but what the problem that I had with my message broker structure was I had a queue that was reflect this data to the database.
Yep.
Right. And that one always had a bottleneck.
Yeah.
Like, and all of these things would be throwing it into that queue.
Yeah.
And that queue would be trying to update the database like 50 bajillion times a second. And those messages would always get kind of stuck there and then everything would fall apart.
So you sort of realize that like storing your data persistently is a whole different set of problems. That's why DBAs and database administrators was like its own role for all of these decades. And it still is because it's a very relevant position.
Yeah.
What you find in that situation is now you're in the realm of like database optimization, not in program optimization.
Yeah, well, I was also using MongoDB rather than anything like, you know. Yeah.
So to be fair, it's quite performant.
Yeah.
Yes. MongoDB's web scale.
Yeah. Oh my god, dude, I forgot about that. MongoDB is web scale.
Yeah, you should put a link to it.
Yeah,
it's an important piece of information.
We're gonna link that. That's great.
Like MongoDB is great, but you also have to understand your access patterns and your data patterns.
Right.
Right. Like,
I'm sorry. I'm sorry. Continue.
So yeah, you need to understand your access, like both your read and write patterns. And I'm assuming in your case, you probably structures like, I have an IP address that is sort of what the key is, and then I have all the metadata is like blah is the big object.
Literally,
right?
yes. Yeah.
And it's kind of good in the sense that it's very simple and it's great for your querying, but it's probably not the best for writing because you're doing a whole bunch of updates to the same keys.
Yeah, exactly.
Right. And you find that not all databases handle that really well. And also, depending on where your database is hosted and how it's being managed, that's its own set of problems, right? You'll find with databases, you're never really bound by networking. You're very much bound by disk read speed, memory bandwidth, how big your caches are, that kind of stuff.
Yeah, and so
and the size of the DB itself,
and the size of its DB.
Yeah, and so I guess I went with Mongo in that scenario, but I see most of the people are going with Postgres.
Yes.
And so, what do you think about that architectural decision? What other,
what was the reasoning behind
what about NoSQL databases versus SQL database when it comes to and I think the model itself of just sort of recon data in general lends itself a little bit better to a highly relational, database and where you can easily draw maps between all of these different objects and have them broken out rather than in like a single JSON blob or something like that. So that's kind of where I went wrong with that. But
I think there's not necessarily a right answer. I know some people want like graph databases as well.
Yeah. That's big. Yeah.
So, I mean, for us, we went for the simple, stupid option. We picked Postgres for our architecture.
Right.
There's some other reasons for that, mainly around how it's being used. Because a lot of the value customers have is like, well, we want to query for data with these properties. We want it to be in this part of infrastructure tagged with this, that are online, that have this port, that have this kind of title. And all of these relational elements is sort of how we built out our schema.
And this is also where NoSQL sucks. It sucks so hard. Like, it's really, really bad at that. Like, it's just like iterating over every single document. It's like, does this match? Does this match? Does this match? Does this match?
So yeah, Postgres is great for that kind of asking those kinds of questions. I think,
dude, I found out about indexes. Changed my life.
Index, okay.
And then I started putting an index on everything, and then it
I'm sure that
my
went
life.
really well.
I was like, let me just index all the things I need to
that'll solve my problem.
I've spent countless hours just staring at Postgres explains, trying to understand why queries are slow. You have multiple phases of optimizing Postgres. Like the first phase is like, okay, chuck an index on it. Then the next phase is like, okay, do I start looking at read replicas or do I start looking at like better hardware? Right. And then it's like, okay, maybe I go with better hardware. But now you start having the problems like, okay, how do I get around the problem that even with indexes, these queries are taking a long time. Right. So what do you do then? Well, maybe I start pre-computing data. Right, maybe I start using things like materialized views. Right, those start solving problems, but then it also creates its own problems, right? Because refreshing materialized views has to happen frequent enough so you have recent data, but then they also consume its own database operations. I mean, at the end of the day, engineering is just a whole bunch of trade-offs, right? It's like, I have this much time and this much effort, and I have this solution I want to get to. How much time and effort can I spend to get to the best solution?
That's really well put, and you're never going to have a fully optimized solution with no trade-offs in that sort of situation.
It's back to that 80-20, right? It's like you start at 80-20 and then maybe 90-10 is where you draw the line because that last 10% for the extra 50% is just for a non-enterprise use case is just not worth it. Like,
it really isn't.
Yeah. Like it's you versus Sean and like,
exactly right.
Just take the L, like 50% of the time.
I did. Thank you. Thank you very much.
And just move on.
That's exactly what I did.
I'm not just go with energies.
Right, exactly.
And I'll just stay there with my takeovers and my day job.
That's my. That was the strategy, man. Yeah. That was the strategy. Oh man.
Coming back to your question in terms of database architecture, Postgres is great. I think you do need to think a little bit about what your schema looks like. One pitfall I didn't realize until very late on is Postgres does really poorly when you repeatedly update the same rows in very, very quick succession. And I think one of the things I would like to have done going back is spent a bit more time thinking about like append only or write only tables and like partitioning those out.
Interesting. Okay.
Because you sort of find that if you, for example, in a very common paradigm is like, I have all these IP addresses, I'll just have a column that says whether they're online or offline. Right. And then maybe I'll add a timestamp of when that happens.
Right.
Say you run a mass scan every hour, right, across all of these IP addresses. You're effectively rewriting this entire table every hour.
Yeah.
Right. And it's like, even if you don't update the true or false for whether it's online or offline, if you update the timestamp and say, I last updated this at this time.
You just finish the last one.
Like the way Postgres works is that when you write a row, unless you have what they call hot tuples, which is some extra space to do small writes, it effectively deletes your row and inserts a new one. Right?
Really?
Yes. So that's how Postgres maintains its asset properties of like when I write something and I haven't finished yet, you don't read partially what I've written. Right? You have your own correct view of the world.
Okay.
Right? So repeatedly updating the same thing will just mean that you're deleting the same row and adding it a whole bunch of times. The way they solve this is what they call vacuuming, which is they clean up rows that have been deleted. right?
Sure.
So you can write to them again. But unless you sort of give it time to do that, if you're writing more than your vacuum is keeping up with, and there's a whole bunch of vacuum tuning stuff that they ask you to do, then you're just going to quickly grow out in space, or your index is going to become something very inefficient because your table is like what they call bloated. It's like every gigabyte of space might only be 100 megabytes actually occupied.
Sure.
So Postgres is great. That being said, depending on what scale, like if you're at a small scale and your database is a couple of gigabytes, no one cares. It doesn't matter.
Right.
But when you're operating like hundreds of gigabytes, terabytes of data, then you have very different questions to answer.
Yeah. No, for sure.
And do you also find benefit, like with a write-only table or a pen-only table, with having almost like a version history essentially of like what's going on over time, like what's changed over time? Yeah.
That being said, it also does grow very, very quickly. Right. So maybe you might look at some solutions like ClickHouse or what they call columnar, I can't pronounce it, the column-based database stores, right? And they compress data slightly differently. They're better for things like that, which is kind of like, I draw the analogy to IoT because you're kind of doing, like, the IT use case is that you use things like ClickHouse to measure temperatures across the world, right? And every second you're recording a new temperature and they add it to this database, and they're very efficient at storing that. I think it's very similar to that because instead of storing temperature, we're storing are things online,
right?
Or what's the status code of this, right? Across millions of things across the world every hour, right? So sometimes that might be a better use case, but it sort of comes with the trade-offs like, well, how do I want to query this?
Yeah.
Right? Am I just interested in what is the latest result? Or am I interested in trends? Or am I interested in slicing up my data depending on which customer is asking?
Yeah. Well, and that's why we kind of ask, because in the beginning it might be, oh, I really want to just like query this from my command line, but also at some day you might want to look at trends, okay, how often are they, rotating these IP addresses? How often are they,
or from a customer's perspective, like when did this exactly change, or why are we noticing this strange behavior? Like, is it flipping on and off? Like,
and we get that question so many times.
Yeah.
I think like for bug bounty people, I think it's a very different question set. And I think what you should be optimizing for is not like this long-term trend use case. It's what information do I need right now and how do I get there, right? And only once you've done that, then can you start iterating on what schema works for your use case.
Sure.
I can't tell you what schema is good because you don't have 5 engineers behind you building this entire system.
Yeah, and you're not an enterprise application.
Yes.
And so I guess let's think about a use case. It's very simple. For example, one of the things that I and we were talking about earlier today with Ryota was, dividing out your domains and your IP addresses logically, and not making your subdomain your primary key, right?
Yeah.
Like that was my biggest architectural mistake I made when I built my recon system. I was obsessed with subdomains.
Yeah.
I was like, a subdomain is the end all be all. But really at the end of the day, it all goes down to IP addresses. I shouldn't say that, but it mostly all goes down to IP addresses.
That's a good point. Because I think
so. This is the kind of discussion I want to have. Is like, what are those mistakes, like focusing on subdomains instead of focusing IP addresses as the lowest level of logical entities, and mapping those, because
I think it also comes to like what kind of recon are you doing, right? And I think subdomains is fine because a lot of things like subdomains is the easiest identifiable way of looking at something.
Yeah.
The reason you say IP addresses is relevant is because there's a whole bunch of assets and like what we consider assets that might not have a subdomain associated, right?
Right.
Like companies like,
or just a subdomain that you don't know.
Right? They don't like they exist on the internet. You just can't see them yet.
But there's also like a whole separate set of pitfalls, like when you start to go to that level, because IPs rotate, like things, subdomains get reassigned. So like you might have an IP address that's stored, and then you scan it, and you're like, oh my god, there's a new service on this. Yeah, it's exploitable, and then it turns out it belongs to somebody else. Like it's not even theirs. And then you report it to the company and they're like, we don't own this IP.
Yeah, that's true. I mean, I think it all depends on, and this is kind of what we were talking about earlier, sort of correlation factors. And I think that could definitely be a new logical entity in a recon structure system, like you have this domain and you've got that, database, what you know about that domain, and you've got this a subdomain, meaning, or FQDN, and then you've got this IP address, and then you've got some sort of relationship between the two of them and how that's correlated. It could be a DNS entry that correlates them. It could be a TLS, SNI, it could be, historical data. It could be, what else could it be? I'm trying to think. What do you think about that?
I've been mulling over this idea for a couple of years, and I've tried to implement this at AssetNote, but the use case is very nuanced, right?
Yeah.
So when you start getting to more and more cloud native apps, the ways you identify what you consider like an asset starts to change very differently.
Yeah.
Right. In a very traditional old school setting, it'll probably be like, we have IP addresses on servers and that's it. We might give them a subdomain. But when you get to like the other end of the spectrum, Uber starts routing things based on your subpath. And if you want to be more specific, Uber starts routing things based on your subpath in a specific geolocation.
Yeah.
Right? So even if you hit the same IP address with the same subdomain, same SNI, same path, you'll be hitting two different data centers that might be running different versions of your app.
Yeah.
Right?
That's true.
Even further, it might be getting feature flagged and routed to another version of the app based on your user ID. Right? And all of these means that at the end of the day, the app you're looking at might not even be the same one. You might be getting like a China version of the Uber app versus a American version of the Uber app.
Sure.
Or even you might be getting a beta Uber app versus the production app.
Right.
And I think factoring all of these into like what you call this correlation,
probably
is overkill for most people.
But I want it to be perfect.
But you want it to be perfect. Well, how about this? For every single company, you create a unique correlation, right? So you build your mental model, you grab Cosmin back and you ask him, how does deploy their apps? Right? And then you work backwards from there. You say, I factor it, doesn't care about geolocation. They don't care about user ID. They care about their tenant ID. They care about their subdomain, whatever. Mm-hmm. But for Uber, totally different story. Now we're in an entire different paradigm. Here's a new correlation method.
Right.
You want to go to the nth degree, you might as well.
I know. No. I mean, you made a perfect point, which is that we can't you so perfectly pointed out that flaw of like, this is just going to be way over engineering some of these things. And at the end of the day, you are gonna, run into these scenarios where you're like, it's not perfect, but then you gotta decide, is the trade-off of that fixing that problem actually going to get me enough bounties to justify the time that I'm spending on it? And the answer to that a lot of the time is no.
I mean, sometimes...
Unless you want to make it your thing.
Yeah, like sometimes it's worthwhile also hacking around it, right?
Right?
You might have this system that works for 90% of the cases, and then you decide, okay, I'm going to spend like 3 weeks looking at Google infrastructure, right? And now this is its entire own beast that has its own books written on it.
Right.
So I'm just going to hack together something that's just for this. And maybe you'll find that I've now spent 3 months on it. I understand it enough. Now I can merge it back into mainline and feed this across the rest of it.
Yeah.
But you don't have to make everything into your giant monolithic beast, right? You can always have smaller pieces that's for something else. And then once you sort of figure out how this works, it then comes back naturally into the rest of the work you're doing.
Yeah. Wow. Yeah. I've, like you said, I have retreated from my recon world into my live hacking event world. And I've just been spending so much time in the hands on the keyboard, manual hacking lately, that I forgot about all the horrendous challenges that there are in the
because it really is an engineering it's an engineering problem. It's an engineering problem space. Like, you have to realize that, like, if you're trying to tackle this problem individually and you're running into struggles and you're not an engineer, well,
that's to be expected.
Yeah, that's to be expected.
Hard.
Like, it's
hard.
Like, literally, there are full-time engineers who spend all day, every day trying to solve this problem.
Yeah.
There are teams of engineers.
Teams. And multiple teams of engineers who spend all day trying to fix this problem and can't, or have to spend weeks, years solving it, right? And so, like, I think, again, like, optimize what you need to optimize for, right?
Yeah.
Like, think about your problem set, think about the context, think about what data do you need for what targets you're focusing on. And if you have to make an optimization, make an optimization. If you don't, just don't do it. You know what I mean? Like, get it where you need it to be and then use it to its fullest. And if it's not enough, then improve.
Yeah.
Or hire a company of people and do it that way.
Right. Yeah. Just become AssetNote.
Exactly.
It's easy.
Awesome. So I guess one of the things that I wanted to bring up as well, just kind of in pursuit of the relentless return to deep technical content, can you give us some wisdom on how to deal with DNS wildcards and what kind of pitfalls we can avoid in that area? And for those of you that are not super familiar with the concept, while I let Sean think for a second, the concept is that some wildcard some domains are
Facebook, good example.
Facebook, Zoom also has it.
Slack, Shopify.
Yeah, there's a lot of wildcards, and essentially what that means is you can put any random string at, what is it, zoom.us or something like that, or slack.com, and it will resolve to an IP address.
Yeah, it's basically anything that lets you generate subdomains, like Shopify, like store.myshopify.com or whatever. Like, the way that all of those route without them creating new DNS entries is that they have one catch-all DNS entry it's a wildcard. And so basically anything dot whatever resolves to like the same set of IP addresses or the same C names, and then that gets routed like in a different way.
And so the biggest problem with that is figuring out, okay, which one of these is a wildcard response, which is always going to be the same and has no interesting data, or which one of these is unique. And that's one of the hardest problems.
Well, I mean, the way we solve it at work is very different from how we solve it in bounties.
Yeah.
When we solve it at work, we have access to your AWS account, so we don't need to guess.
Right.
So we can save a whole bunch of energy. And
beautiful. Love that for you.
In bounties.
Let me just ask for the
exactly
account ID real quick.
Yeah, like, can you just give us your DNS record? But in the bug bounty space, we do it at resolve time. Like, we build our own custom resolver that does all the like resolution checking, and it pretty much like does wildcard detection every layer, right? So at every depth of the subdomain, we start trying to detect, is this a wildcard or not? We figure out like what is expected to be a wildcard, what isn't a wildcard, and then it kind of depends on what you're optimizing for at that point. Are you willing to resolve millions of attempts to find that one or two records that is true or not? Or do you just discard this entire set and move on to the next
Which
set?
Once again, those are both viable options. I've done both of those before, and they both result in great things. One, because you're if you do actually go through the weeds, it results in you finding hosts that no one else finds because they're not willing to dig through the weeds. Yeah. But if you don't and you ignore that whole thing, you save hours and hours and hours of time that you would solving one of the hardest problems that you run into.
Yeah, because at face value, it's like the simplest way is ignore it or look through every single one.
Yeah.
Right? And it's like neither of those options are super great. One's super tedious and the other leaves a gap. And so,
well, it's only tedious when it's slow. But if you hypothetically could resolve millions of results a second.
Yeah. Hypothetically, of course.
Right. Then
if only there was a company that did that.
Yeah.
Right. Then
exactly. Right.
You don't need to like have the trade-off, right? Just resolve millions of results a second.
Yeah. So that goes back to the optimization problem too. And I want to say, I haven't looked at this code in a really long time, but I want to say when I tried to solve this problem and actually tried to be able to weed out all the wildcards, I actually resolved a certain subdomain. And then I appended something to it and resolved it a couple times as well and compared the result. And so for every single entry that I was doing, I was resolving, 3 or 4 times. So it was growing, linearly in that capacity. Right. And it was also, there was that. And then there was another piece of it. Because you can cache it a little bit with saying, okay, I've already sort of figured out whether this level of the subdomain is a wildcard or not. But then you run into scenarios where you've got like subdomain dash everything wildcard, right? And then it's going to blow up your database again if you do it. So
the answer to everything in computer science is a hash map. So hash map everything.
Everything.
You just hash map all the wildcards for every single level. Yeah. And then now you can just start matching against every corresponding level and see how far you get. That's relevant.
Yeah. What a beautiful structure, the hash map.
Oh, I love it.
It's lovely, man. Yeah. No, that is good advice though. So you're saying, let's just take Uber, for example, uber.com, test.uber.com. Okay. I've determined test.uber.com is not and then, you've got abc.uber.com. Okay, that is a wild card. Yeah. And then you can continue to grow as the subdomains change, and you at some point you will have already resolved that, or you can quickly resolve that and you're good to go.
Yeah.
Okay. We are getting the signal from our manager right now that it's time to wrap up this episode.
Yes.
Sean, dude, thanks for coming on, man.
Thank you for letting us pick your brain.
We will definitely have Sean on again.
Not like this though. We're gonna have to do it over Zoom because
I mean, as much as I'd like to fly me to the States,
we'll just fly you out with all of our crazy critical thinking budget. You got anything you wanna shill to the people?
don't try to solve hard problems if you don't have to.
Yeah.
And don't try to find hard bugs when you can find easy ones.
Yeah.
And where can they find AssetNote?
Yeah.
You can find AssetNote
At AssetNote.com.
AssetNote.com, AssetNote.io. You can find us on Twitter at, I think, like at AssetNote probably.
Yeah.
And then you can find me on Twitter at Sean Yeoh, I think.
Is it Sean Yeoh? Do we need to check that really quick, or are you feeling pretty confident about that?
I'm not confident.
Okay.
I only shitpost on Twitter. There's nothing useful there.
We'll put it down below. Don't worry.
At Sean Yeoh.
Okay.
Awesome. Okay. There we go. All right. That's a wrap.
Awesome. That's a wrap. Peace.